All right, everybody. Hi, and welcome to this month's Astronomy on Tap. It is February, and we just had our, lovely Valentine's Day. So I hope you all have enjoyed our tip war theme. And it will be a interesting tip war. So we have our Heart on Pluto mixed with our Rose Nebula. So pick your favorite object. Send some good tips our way. We really like to. It keeps us going, keeps us motivated to continue this, and also it's some pretty fun topics. But we have some awesome speakers here today, and I'm sure you've noticed if you've been to multiple shows before, you've noticed Courtney being the MC for the evening. Courtney is not here, obviously. My name is Ashley, and I will be the future MC for the next several events. So I'm super excited to be here, and I hope you are too. So before we get started, just a quick reminder, be respectful in the chat. As you're typing, you're welcome to post questions, kind of chat with other viewers, everything like that. But please be respectful, nothing rude, nothing inappropriate. We've never had an issue before, so let's not start now, and hopefully we won't have any issues tonight. But we can go ahead and introduce our first speaker of the night. We have Dr. Caitlin Ahrens. She is involved in a lot of really awesome stuff. And so her research involves remote sensing of icy surfaces and volatile interactions. Caitlin also works on a number of planetary volcanism projects, including lava flow, morphology, caldera formation, and rheology on Mars, Ceres, Titan, and Pluto. So tying in with our tip war here. She received her bachelor's in physics and geology from West Virginia University and a PhD in space and planetary science at the University of Arkansas. Caitlin is currently a NASA postdoctoral program fellow at NASA Goddard Space Flight Center. In 2018, Dr. Ahrens received the 10 Outstanding Young Americans Award for her efforts in science communication and outreach. She also likes jigsaw puzzles and knitting hats for cancer patients. So please join me in welcoming our speaker, Dr. Caitlin Ahrens.
Thank you so much, Ashley, for that amazing introduction. I'm so excited to be here. Whenever we first started emailing each other about this event, I was like, yes, I get to finally be involved with a virtual astronomy on tap. So this is really exciting. So what I'll be talking about tonight is space volcanoes, which, if you imagine, is much more difficult than I actually make it out to be, but I promise it's way more fun. I also need screen sharing capabilities, hosts. So while that's being figured out in the meantime, that was very quick. Oh goodness, my computer could not handle the quickness. Thank you, hosts. All right, so let's get right to it, shall we? So wild and wonderful space volcanoes. Off we go. So if I were to ask you, imagine what is a volcano. If I were to ask you, quickly draw a volcano, almost like Pictionary style, you would probably end up with something like this. Just something very mountain-shaped looking, almost kind of concave looking, some sort of fire activity spewing out of it, maybe some ash and clouds, maybe something dribbling out of the top of it. But we imagine some sort of activity and something that's usually pretty red hot stuff just spewing out of the earth. And in a sense, that's partially correct. So we're going to kind of view how that's partially right for the solar system and how weird the solar system volcanoes can actually be. So in terrestrial definitions, a volcano is some sort of mountain or hill, typically conical, having some sort of vent at the top, which some sort of lava or rock fragments or vapor and gas mixtures can erupt out of that vent. So again, true to form, this is a very classical example. This is from the Mauna Loa and Mauna Kea regions out in Hawaii. So you see a lot of activity. You see just from this image alone, just how hot this image can be, and just the different morphology of the lava. But even on Earth, there's so many different structures and kinds of volcanoes. And that's something that we need to keep in mind whenever we're studying other volcanoes on other planets and moons, is that we always try to come back to Earth and try to compare it to our own structures, mainly because it's easier for us to go to the volcanoes in Hawaii and Iceland and figure out how did those form, that rather than trying to travel all the way to Mercury or to Mars and even out to Pluto. So space-time, or as I like to call pretty picture time. So we're going to start with planet numero uno, Mercury. So Mercury does not have beautiful mountains or anything. There's no vents or anything. You just have these kind of weird ancient puddles, if you will. So these are just essentially just filled in plains. Now, how these may have formed is that you would pinprick the surface enough times, and essentially Mercury would have bled out. So essentially, these are just scab wounds on poor Mercury here. So all of this, though, can still tell us a lot about what would have been the inside of Mercury. How fast would it have, essentially bled out, but then frozen over and scabbed over all across the surface of Mercury. So Venus is a little bit of a tricky planet because of its thick, luscious atmosphere. But there are more than 1,000 volcanoes just all over the surface of Venus. As far as we can tell, the resolution that we have with from previous Venus missions haven't been stellar. So hopefully by the 2030s, whenever we get our beautiful 3 Venus missions coming up, 2 from NASA, 1 from the European Space Agency, maybe the resolution will be so much better and we can learn more about these volcanic systems. However, they're more than likely dead, or at least very dormant. Now, there's a lot of debate as to whether some of them are still geologically young as well. So looking at what kinds of lava flows are we dealing with, though. But again, big, luscious atmosphere really took us a while to figure out, what does the surface actually look like? Now, do we actually wish the surface of Venus was this colorful? Absolutely. Who wouldn't want a planet to look this gorgeous and beautiful and rainbow? But no, so this is a topography map. So all the white areas and the pinker areas, those are the higher elevations. Your purples and blues and darker colors are your lower elevations. So there's a lot of equatorial elevation going on here. And you have your variety, your pancakes, sticks, and shields. So pancakes, think of these as almost like little pimples all across Venus. So Venus is going through some hormonal changes here, but so pancakes, if you will, then are just little suction cups of material that just kind of slowly pockets upward and then almost fizzles out at the edges. Now, sometimes those pancakes can get larger and larger and larger, and so large that the crust underneath those pancakes just can't quite hold on, and they crack. And because the surface cracks around the pancake, it looks like a bug and it looks like legs. So we call these ticks, in which case these are much larger pancake formations. And then you have your shield volcanoes. So this is an excellent example. This is Mont Mons, which is the largest volcano on Venus. So lunar volcanism is interesting, to say the least. There's 2 main parts of lunar volcanism. You have the really gorgeous, beautiful, smoother, darker mare, Latin for oceans. There for a while, we truly thought that the moon had these gorgeous, beautiful, dark black oceans and everything, though. But no, these are actually just lava plains. It's similar to Mercury, where you have just a lot of internal magma just pushed outward. But unlike Mercury, the moon wasn't pinpricked a million times. Instead, you have that tidal force with the Earth, and all of that material would have kind of flushed forward. So the moon's face is always facing us. This is called tidal lock. And so if we were to see the far side of the moon, we wouldn't get as much of these mare on the far side. There's like little bits and pieces, but it's not so bad. Another type of lunar volcanism, though, are lunar domes. And these are very fascinating because we want to go explore what's the mineralogy behind these like little lunar domes. So some of them are very rocky looking and rugged and sharp, and then some of them are very low lying little, well, moon pimples. There. Now, Mars, I can talk about for hours on end. My goodness, the volcanology on Mars is just amazing. You typically have shield volcanoes, so very low, slopey looking volcanic structures, nothing, too fantastic, but they are immense. The most notable one seen in the upper left here on Mars, though, that is the largest volcano not only on Mars, but it's the largest volcano in the whole solar system. So this is Olympus Mons. Now, funny thing about Olympus Mons, though, I'll get to here in a bit, but back to using Earth as our playground to understand Mars volcanology, or just volcanology in general. So these are just a couple photographs between Mars on the left and Earth systems on the right. And so we can go visit these places on Earth to get a better understanding of, hey, you know what? We see the same thing on Mars, but in Iceland. So, what's going on there? All right. So quick little fun fact about Olympus Mons. We had completely missed it. 1964 all the way to 1973. Mariner 4, 6, 7, 8, and 9. They all missed Olympus Mons. They got maybe like the very tip of the flank, but not enough to go, oh, that's a big volcano there. We should do more stuff with it. It wasn't until Viking 1 and 2 in 1975, finally, first successful U.S. landers onto Mars, landed on opposite sides of the planet. But as it was going toward the planet, they're like, oh, hey, look at there. That's a big volcano. How about that? So here is our beautiful Olympus Mons. So like I said, very slow flank. So it seems steep in this particular image. But if you were to actually go there and then walk, it takes a while. So the base of this thing is about the state of Arizona. And height-wise, it's quite big, quite tall. So it's a very complex, interesting volcanic system, to be sure. It also shares the neighborhood with 3 lovely other Tharsis region volcanoes here as well. Now, why they are aligned is still very interesting to research as well, because we're thinking, how do hotspots work on Mars when there's no immediate plate tectonics, as opposed to Earth? You have very active plates. You have hotspots at, like, say, Hawaii or even in Indonesia. So comparing those planet systems again can really help. So Tharsis region, it's all of this red and white stuff going on here. So this is just a big honking rise of crustal material to kind of compensate for these large volcanoes. But if we were to look at a geologic map of Mars, and yes, every single color that you see here is a different geology. This is why Mars is just so beautiful and complex. But all of the really bright pink regions off to the left here, that is all lava fields and whatnot. You notice maybe some pink off to the right here, and that is part of Elysium Mons. Real quick, I'm going to touch real quick base on Ceres. So Ceres is the large dwarf planet in the asteroid belt, and poor Ahuna Mons, the lonely mountain, sad face. So Ahuna is the only mountain like this on Ceres, and there's a couple theories going on here, but we see a lot of salt. with this particular mountain. So could it be some sort of like a large salt dome kind of thing? Maybe. Do we consider that to be volcanism? Yes, because it would have had to have been some sort of subsurface stuff, gunk, salt stuff to rise up and make this kind of dome. Io. Oh, goodness. So Io is very, very sticky and squishy and very volcanically active little moon of Jupiter. It's incredibly sulfur-based, and sulfur is a very, very soft mineral. It's also very smelly as well. So you can imagine the smell of Io whatsoever. Yes, gotta love that smell of Io in the morning. But very, very active, though. And we have seen two separate vapor plume eruptions from two separate missions just happened to fly by Io, and Io decided to just kind of do a little bit of a blip to those missions. So one in 1997, that was the Galileo mission. That's shown here on the left. And then the New Horizons mission when it got to Jupiter around 2007. But this is a close-up of what the volcanic systems on Io look like. Definitely not mountains. Like I said, the sulfur compounds are incredibly squishy, so not enough to make beautiful, gorgeous mountains or anything, but essentially just these large, irregular cavities that once opening up, they would release some sort of geyser-like material and then just kind of ooze and scab back over. So now we're getting into my lovely cup of tea here, which is cryovolcanism. So cryo meaning ice, but then how do you make ice? Just very simple ices. You can have water ice, you can have nitrogen, methane, carbon dioxide, carbon monoxide, sometimes ethane. How do you make just very simple frozen stuff behave and bend and structure itself to mountains and glaciers and valleys, and yes, even volcanic systems? So this is where cryovolcanism can get really fun and really complicated very quickly. So there's really no exact definition of cryovolcanoes. It's just, does it look like a volcano? Does it quack like a duck kind of deal? And is it cold? And that's essentially as far as we got. So what do we consider to be different kinds of ice structures? How do we even get a sense of comparison anymore? You have Titan and Triton and Pluto, and then a whole bunch of other icy moons as well. And then what kind of materials are we dealing with here? And then cryolava? Question mark. So back in 2018, there was a workshop all about cryovolcanism in the solar system, just to purely give it like a think tank notion as to like, okay, we're going to have a definition. We walked out of that workshop. It was like a 4 or 5 day workshop. And if anything, we left with more questions than answers. But that's fine. That is absolutely fine, because then it gave us more stuff to do in the meantime. But Sarah Fadgens in 2018 had this amazing work on what are the different ways that ice can pop up to the surface, whether it makes beautiful geysers or just sticky, oozing cryolava all over the place. And turns out there's many different ways. I'm not going to go through all of these, but you can have anything from warm ices rising up and then cooling down, and you have some sort of convection. Exsolution means bubbling kind of action, which is always very fun. Fracture propagation, so you'd have the surface essentially crack open, and then some sort of fluid would have had to burst forward to make the cracking, and very dynamic. So I'm going to talk very briefly about Europa and Enceladus, because I know my partner speaker would probably be talking more about these lovely moons, though. But I do want to touch base real quick on these little salt domes on Europa. They're so cute and so tiny. Yes, more moon pimples here. But do we consider these to be cryovolcanic? Yes, in a sense. Again, very similar to Ahuna Mons on Ceres, is just bunches of little solution, watery, briny stuff just kind of popping up on the surface. Real quick then too, Enceladus. So Enceladus, the tiger stripes in the southern hemisphere almost have like a breathing action to it. They kind of open up and then close and open up and close. They're very, very thermally hot. And then whenever they do open, they breathe out. They let out these enormous active geysers, a couple kilometers worth into the sky. Titan. So Titan, Saturn's largest moon, very, very gorgeous and very complex moon. Now, Titan kind of takes the cake on being the weird moon here because you have a very luscious atmosphere. So we really don't have that really good of data on Titan's surface, unfortunately. So whatever we do have is kind of hand wavy and just going like, well, that kind of looks like a mountain there. It may be a cryovolcano or just a really pretty mountain. But there are some radar images that, this is certainly a mountain. This could be kind of a vent looking system. And then could this essentially be kind of a cryo lava goop kind of spilling out of it? Maybe. We need more data though. So, Triton. So Triton is absolutely gorgeous. Unfortunately, these are very, very few and beautiful pics that we have from the Voyager 2 back in 1989. So I mean, it very, very sparingly images, but what we were able to capture are two major instances of cryovolcanism. The first one being these puddles. So let's see. Yep. So that's a crater. But all of this little knobby looking stuff in the middle, that may have been a vent. And it kind of all over the place and filled up this basin. And yes, I'm gonna, that's the technical term. There. And then in the southern hemisphere of Triton, you also have these black streaks. There for a while, it was like, what surface feature is this? Why is there stripes on Triton? What's going on here? And turns out these are also geysers as well. Now, the debate going on now is, we know these are nitrogen and methane and carbon dioxide geysers. The nitrogen nitrogen mixed with carbon dioxide actually makes it kind of that darker, dusty color. But the debate is, are they considered exogenic or endogenic? Endogenic meaning the tidal forces within Neptune or within Triton are being pulled by Neptune. And so are the poor little insides of Triton just kind of getting constantly pulled and geysers erupt? Or is it exogenic, where a radiation all the way from the sun, millions and millions and millions of miles away, but yes, solar radiation can still go way past Pluto, and is the surface of Triton essentially getting sunburned to the point where the very top layers of ice are just getting sublimated away and it pops out all these tiny little geysers. And Pluto, very, very beautiful Pluto, though. So New Horizons got to Pluto in summer of 2015, gave us our very first beautiful high definition images of Pluto. Now, what was interesting is this particular region of Pluto, this is closer to, well, the southern hemisphere of Pluto. This would be right Mons, this big chunky looking donut looking thing here. And then right at the very shadow part here, that's the rim of Picard Mons. Now, just looking at this image in general, this would look like a very classical looking cryovolcano. You would have some sort of big mountain. When I mean big, though, the height of right Mons is only about 4 kilometers or 2.5 miles tall. So really not that big. But comparison to everything else geologically around this area, it's pretty large. So 2.5 mile large mountain with a vent in the middle and then just some sort of texture looking lava around it. This looks like a very interesting, closed textbook case of a cryovolcano. But what makes the cryo lava? And that's the fun part. So it turns out the more ammonia that you have at very low temperatures, it lowers the freezing point of a lot of different ices, specifically water ice in general. So the more ammonia that you have at low temperatures, the more slushy you're going to get. Now, the interesting part, the more methane you start to add to the mix, your whole system just becomes way too watery and oversaturated. So having some sort of big structure like this, you would have to have a lot of water ice and just only a little bit of ammonia and methane to make it chunky and spread like that. So there are plenty of questions to explore with cryovolcanism. This is obviously just a very, very short list. But we want to understand what makes the different flows. Why chunky on Pluto, but then why almost smooth and not so crater-like on, say, Triton? Could lava tubes on the moon and even Mars, could they have some sort of astrobiological implications? What role does salt play in a lot of the icy moons, such as Europa and Enceladus? And even Titan. Titan has its own variations of salt as well. So all of these different kinds of chemistry and physics, thermodynamics, all of these different kinds of planetary sciences really need to work together. And it's still an interesting mystery, to be sure. Real quick, though, we do have a couple missions coming up for icy bodies. We got Europa Clipper coming up, and then we also have Dragonfly for Titan. Woohoo! So Dragonfly is going to be a nice little quadcopter laboratory that's going to bounce around the surface of Titan. Now, is one of its objectives cryovolcanism? No. But can we better understand the chemistry of the surface of Titan? Yes. So it's kind of stepping in the right direction there. Also, a brand new Mars volcanology textbook just came out through Springer, which is Mars, a Volcanic World. And I will, can't wait to answer any questions that everyone may have. Thank you again for having me this evening.
All right. So I thank you so much for that awesome talk. We did have a question or two in the chat, and then of course we have some. We definitely have some other questions for you. So I will go ahead and turn off my camera so you can keep yours on. And just have myself kind of be unmuted so you can still hear the questions. And for everybody watching, if you have questions, now is the time to put them in the chat. I will be the one fielding questions and asking them to our speakers. So please feel free to, if you have a question, no question is, any question is good. So go ahead and put those in the chat for us. So we'll go ahead and get started with why are there less mare on the far side of the moon?
Very good question. So since the moon is always facing us because of tidal lock, so the Earth and moon always facing each other, because of that interesting dynamic of movement, the Earth being so much bigger, it's also causing so much of a gravity pull with the moon. And so the poor insides of the moon are gravitationally attracted toward the Earth. So when the moon was just starting to form and everything, its insides were still very slushy and gorgeous and moving and everything. But with that gravitational pull of the Earth, all of its insides decided just to lopsided off to the side there. So that's why we have a lot of that mare magma stuff on that surface, on our side of the moon. But yeah, there are still like little pockets of mare spots on the far side.
Awesome. So we have another question. We have here on Earth, you usually hear that volcanoes go with plate tectonics. Is that true on other planets and moons, and why or why not?
So that's the fun part. It's no. So yes, we do have plate tectonics where our plates are very much just moving jigsaw puzzles. So that's the fun, tricky part about the rest of the volcanic systems is what makes the crust move or not. So you have different flavors, if you will, of crustal systems. So you can have what's called stagnant lid. You can have almost like a plastic lid. That would be more Venus type. It's so hot on its crust. It's very, well, plasticky. In a sense, it's very blocky with its volcanic systems. On Mars, you would have hot spots. So some sort of magma chamber that would just plop up all of its material and form a volcano. But then how would the hot spot move or the crust move and slide, and then the next hot spot moves, and then the next hot spot? We have multiple hot spots? That's also an interesting theory as well. How do we get those little salt domes only in one part of Europa and maybe even Enceladus, but maybe not the whole thing? So all of these different kinds of questions are still being explored.
Awesome. So we actually have a question, another one. So have any of these planets and moons been found to have an atmosphere? Sorry for that. And if not, could the vacuum of space play a role in the essential pulling of the cryomaterial to the surface?
Ooh, very good question. So yes, it kind of boils down to what do we define as an atmosphere? So it can get very entertaining of whether people think an exosphere is considered an atmosphere, and then it depends upon what physics you're dealing with here. But Titan, it definitely has a very thick, luscious atmosphere, nearly a little bit over the same surface pressure as here on Earth. Actually, we have 1 bar pressure, surface pressure. On Titan, it's about 1.5 bars of pressure. Nice, thick, heavy atmosphere. Pluto is considered to also have an atmosphere as well, in very hazy, thin layers. So not as thick. It's very, very thin. And even Mars is considered to have a very, very thin, practically transient atmosphere. So there's different layers of atmospheres. But then going back to your question on what happens with that material. So it kind of depends upon, does the material just kind of ooze out? In which case the atmosphere wouldn't really play that terribly big of a role. In the sense of Pluto's atmosphere and even Titan's atmosphere, for example, there's some really complex chemistry going on in the atmosphere that kind of clumps very heavy organic materials in its atmosphere, and it can fall, but it won't do much with the cryolava gooiness. But then the geysers, very active, spewing forth very rapidly out into the sky. Yeah, you're not going to get much of that back. So this kind of gets into Enceladus almost supplying a lot of the ring particles around Saturn, if you will. We call this the E-ring around Saturn. So a lot of that could have been through geysers and also impacts as well, with all the icy bodies. If you impact something and chunks of ice kind of fall forward, you're not going to get much of that to come back down. Some of it will, but a lot of that will just kind of vaporize off and make itself somewhere else.
Awesome. Okay, so we're definitely getting more questions the more questions you answer. So, all right, can you get volcanoes on asteroids?
Whoa, well, so Ceres is kind of an interesting way to put that. So technically, yes, with Ceres, even though it's a dwarf planet, but semantics, the titles don't matter, don't mean a thing. But have we found volcanism on Vesta? Not necessarily. Have we found volcanism on other asteroids per se? Not really, because asteroids are very irregular. They're usually not beautifully round like Ceres is. They're also really not that big. Now, Could asteroids be once part of a volcanic world? Absolutely. So Psyche is a very good example of this. It's a very heavy metallic asteroid. And soon to have its own mission, the Psyche mission coming up. Yay. But because there's a lot of metal with it, it may have been some sort of core or even very higher iron heavy volcanic protoplanet at some point. So is there volcanic systems on asteroids now? No.
Awesome. All right. Have cryovolcanoes ever existed on Earth?
Ooh, very good question. So going back to snowball Earth times, then we probably wouldn't describe that as cryovolcanism, honestly, because Earth would always have been some sort of heavier metal crust. Cryovolcanism is specifically only for crusts that are lighter materials and ice. So lighter materials being more like barely touching on aluminum. Think silicates, think quartz. So think very much lighter silicate materials in that regard. Maybe, yeah, aluminum, nickel, very lighter metals and materials, barely. Farther out you go, you're just dealing with pure ice from there. But on Earth, you're dealing with much heavier metals. You're a terrestrial planet. You have more iron and magnesium in your baby Earth crust to pop out the volcanoes and everything. So probably not cryovolcanic. Could they have been cold, like the volcanic systems on Iceland? Yeah, but we wouldn't call them cryovolcanoes. We just call them just nice, cold, but still very hot and fiery volcanoes.
Awesome. Okay, are cryovolcanoes destructive just as volcanic eruptions are on Earth?
Oh, well, they can be. So the geysers would certainly be an interesting thing to behold if you were very much up close and personal to them. It would probably be just as devastating if you were near the Yellowstone geyser. Beautiful, but you wouldn't want to be on top of it at that point. So probably very hot, very salty kind of deal. Now, the further out you go, say like the cryovolcanoes on Triton and Pluto, when you have more ammonia, that stuff is corrosive. That stuff can get very, very sticky, and it's very slow. So it wouldn't be quicksand or anything like that, but very, very corrosive though. So don't poke it.
So definitely some different ways of destruction. Okay, so recently some scientists suggested building a giant gravitational wave detector on the moon because it is relatively quiet. Do you think the moon is a good location for this?
Sure, I don't see why not. Especially if it's maybe on the farther side of the moon, if they want that kind of peace and quiet. The lunar poles could be quiet. It depends upon what all you're wanting to do with gravity waves. Probably far side of the moon for communication and sensitivity of instruments with those, you would need far side of the moon. But volcanic systems, the moon wouldn't be that volcanically active anymore. There's still moon quakes, but they're very, very minor magnitude. So that shouldn't be of any worry, considering we know how to deal with like the LIGO laser systems here on Earth, which is a very active earthquake heavy planet. If we know how to deal with those kind of laser systems on an ever moving active planet, I think putting them on the moon should be maybe a little bit easier.
Awesome. Okay, so we have two more questions. One is, how do volcanoes erode differently on Venus and Titan when compared to Earth?
Beautiful question. So it's all in the material. It's all in the chemistry. So Venus, you're dealing with Iron is practically a protein shake on the surface of Venus. It's so hot that anything heavier than iron can slush, and it can turn liquid, and just, oh my goodness, so heavy metal on Venus. Now, what does that mean for the crust of Venus and everything? We're still trying to figure that out, especially in a laboratory setting, safely, because that is extremely dangerous to deal with. But trying to deal with the different kinds of minerals and reaching very high temperatures and high pressures like that. So Earth, again, being 1 bar, Titan being 1.5 bar, you're doing a 90 bar on Venus. Very much crushing pressures there. So the mineralogy may be a bit different. Your iron type minerals, we know that there's some bits and pieces of olivine, which we have here in Earth's mantle as well. Anybody out there in August birthstone, that's olivine, it's peridot. So on Venus, though, all of those metals just kind of crunching together and being slushy like that. Yeah, this is why pancake structures are kind of dome-like. You just get that slushiness build up and then crack the surface, and they make themselves into ticks. Whereas on Titan, again, we don't really 100% know how many volcanoes are on the surface of Titan. We need more images on Titan. But we have a pretty good understanding of the chemistry of Titan. You have a lot of ice. You're not dealing with any metals there. It's just pure ice and a little bit of organic gunk on there too. It kind of gunks up the works literally. But there's also bubble systems on Titan. We know this through experimental research as well. So could those volcanic systems bubble up or sludge up? And that we still don't know.
Awesome. Okay, so now for, of course, our very most important question of the night. It is tradition for the Astronomy on Tap speakers to answer our question. Thanks to our lovely audience member. What is your favorite Pokemon?
Okay, I love Ponyta.
Perfect. It's a very good Pokemon. Yes. All right. Thank you so much for attending and giving us giving this amazing talk and answering all of these awesome questions to those. And so now we can go ahead and switch our cameras. So now we will move into a brief intermission, about 5 or so minutes to give everybody a break to go get, refill your drink, get some water, maybe get another drink, use the bathroom, do what you need to do. We will be back online for Dr. Jessica's talk, and we will be back briefly. All right, everybody, welcome back to our second half of AOT February edition. So thank you so much for coming by. And if you're just logging on, we had an awesome talk by Dr. Caitlin Ahrens about planetary volcanism. And we have our next amazing speaker, Dr. Jessica Noviello. And we will go ahead and introduce her. So she is the NASA Postdoctoral Management Program Fellow working for the Nexus for Exoplanet System Science, a research coordination network in the NASA Astrobiology Program. She's an expert on ocean worlds of the solar system, both past and present. If she isn't working on something NASA related, she might be out hiking or digging up fossils somewhere in the southwestern United States. So please give it up for Dr. Jessica Noviello.
Thank you so much. Oh, this is fun. I was listening to Caitlin's introduction and I thought, oh, wow, there were so many good details in there that I should really include, like that I got my PhD in 2019 from Arizona State University. Very proud Sun Devil over here. So, but without further ado, let's start talking about ocean worlds. I think that if you were here for Caitlin's talk earlier, you're going to see a few of the same ideas repeated. You're going to hear a lot about cryovolcanism from me this time, but it's such a cool process. I hope you don't mind because, I mean, it really is just awesome and it's everywhere. And it turns out that it is an important clue for how we think about exoplanets as well. We'll get there, I promise. So first off, let us define what an ocean world is. So the official definition is that it is a planetary terrestrial body that contains a substantial amount of water as hydrosphere or something like an ocean on its surface or as a subsurface ocean. So a hydrosphere would be something like what we have here on Earth, but a subsurface ocean would be something like the ocean underneath Europa's icy shell, Europa being one of the most famous moons of Jupiter. And it's actually the body that I got my dissertation on. I can tell you all about Europa's geology. I can tell you about what it means. But a lot of times when we talk about Europa, we are putting it out there as a classic example of an ocean world because it was one of the first places that we confirmed the presence of liquid water in our solar system. That liquid water was really interesting because a lot of people looked at it and said, hey, liquid water is a component of life. It's necessary for life here on Earth. Maybe it's necessary for life in other places. Therefore, could Europa be a place where life in the solar system exists outside of Earth? Not necessarily aliens, nothing to the extent of a civilization. I think we would have seen evidence of that by now. But something very simple like multicellular organisms or even unicellular organisms could be possible somewhere in Europa's surface. And when we talk about life on other planets, that's what astrobiology is. And at this point, it's mostly just the search for life. But again, if we're talking about exoplanets, which we will at the end of the talk, we're going to see a lot more potential than we might see here in our own solar system. But wait. I think I'm getting a little bit ahead of myself because how is it that water came to exist in our solar system in the first place? And why is it's kind of unfair that this is the case, actually, because we're here on Earth and our oceans are awesome. I'm not knocking them at all. But it's a little unfair that all of the ocean worlds in our solar system seem to be so far away. So why is that? And that comes down to how solar systems actually form, and not just ours, but all of the ones that we see around other stars as well. When a star is very young, it's generally a lot more active. It's hotter, it's bigger, it's more energetic, it's throwing off more radiation and more solar flares. And so the environment around the sun is a lot more hostile. It's hotter, it's more radiation heavy. Liquid water cannot condense if it's too close to the star. So what we call this line in the mix of dust and gas that surrounds a baby star, the inner limit for liquid water to condense is something called the frost line or the snow line. And I should clarify here that when we talk about the frost line, I'm specifically talking about the line for water. For different volatiles like methane or nitrogen or even carbon dioxide, those would have different condensation lines going out even farther away from the sun. So this is there are so many details that I'm glossing over here, but generally you can use it as a rule of thumb where the dust and the gas and the planets inside of the frost line, they generally don't have a lot of water on them when they first form. But then anything outside of the frost line is a lot more likely to be enriched in liquid water, or at least solid water. The heat and how it melts is a totally different story and a very different dissertation. But then if Earth formed inside of the frost line, where did Earth's oceans come from? Of course, we have a lot of water here on Earth. It's necessary for life here on Earth. And it's a very valuable resource, especially in a place like Arizona. So we know from studies done with Earth geology that Earth has had liquid water on its surface for at least 3.8 billion years. But where did it come from if Earth didn't start with it? So the big idea in the beginning of, well, I say the beginning, but we have known for a while that comets are made of ice, and ice is liquid water. So it kind of made sense for a while that, oh, well, in the beginning, a bunch of comets hit Earth and that's how the water got here. We have a lovely introduction from my cat as well. So unfortunately, when we went and we got better sampling from actual comets, like we actually sent a mission up there and we took samples of its composition, we found that the composition of the comets did not actually match the composition of Earth's oceans. So maybe comets weren't the actual source of Earth's water. So we thought, well, maybe asteroids? We'll come back to that because it could be asteroids, and that's a really interesting thought. But recent evidence has come out that maybe it was Earth itself, that may be in the form of hydrated minerals. These are specific minerals that actually have individual water molecules locked up in their mineral structures. Maybe that is where Earth's water came from. And it's one of these ideas, or one of these papers that put forth this idea, actually argued that there are so many of these hydrated minerals out in Earth's mantle, in that big layer between the core and the crust, that it could be up to 10 times the amount of water that's on the surface right now. So why do we think asteroids, and how are we going to test this idea? We actually have a mission right now, and I say we, but I really mean NASA, has a mission called OSIRIS-REx that is actually going to it's actually a mission that's going, and actually it went to this asteroid 101955 Bennu. It is currently on its way back with a sample of the asteroid actually contained within it. And it's, I think, more of a sample than they expected to get, which is wonderful news. So we're going to take that information and we're going to analyze the contents of the OSIRIS-REx mission. We're going to analyze the composition, and we're going to figure out if maybe this type of asteroid, maybe not this specific one, but this type of asteroid could have helped originate Earth's oceans. Unfortunately, we're going to have to wait until 2023 to get that information back, and then we're going to have to spend months analyzing it. But, you know, it's on its way. So we're making progress here. So let's go back to the classic example of an ocean world, my favorite, Europa. You might notice that the surface of Europa is covered in this red gunk. This red gunk is actually salt. Exactly what kind of salt, we're not 100% sure, but many studies are out. And I think I saw one last week arguing that it was sodium chloride or table salt. Now, I haven't read that paper yet, but I can believe it. What's interesting about the fact that there's salt on the surface of Europa is that we know that there's salt inside of the ocean. And we know that because as Europa orbits around Jupiter, it actually creates its own magnetic field. And it could only do that if there was some kind of polarized chemical inside of the ocean. And it has to be a salt. That is by definition a polarized molecule. So what we think is that, well, what we know happened actually is that somehow the salt from the inside made it all the way to the outside. How could that have happened? So here are some ideas for how water reaches the surface on Europa, and you might have heard some of these ideas from Caitlin before. The first is something called diapurism, where a whole bunch of mass just moves from the bottom of a thick ice shell all the way up to the top. Maybe. Here's another idea. Here's cryovolcanism. Again, maybe. You've already met Ahuna Mons from Ceres. Caitlin talked about that. And this is effectively an ice volcano or a cryovolcano. So the dark moats that are around some of these features could actually be evidence of a cryovolcanic flow, and the domes themselves in the middle of these features could be the cryodome or the cryovolcanoes themselves. But then the final idea is something called liquid water sills. And again, I'm oversimplifying here, but the basic idea is that there are pockets of liquid water trapped within the ice shell itself, and that different amounts of pressure and the changing ice shell itself is actually pushing water to the surface. And that salty water gets to the surface, the liquid water evaporates or it sublimates away, but the salt remains. So these are all ideas that are out there. But what's really cool, and what I'm going to focus on for a few minutes now, is the cryovolcanism. Now, again, we have just heard an excellent explanation from Dr. Caitlin Ahrens before, but just in case you are just tuning in, cryovolcanism is the effusion or even potentially explosion of a slurry of material off of a planetary surface, but it has to be a water-based material. That's pretty critical. And it's usually mixed in with something like ammonia, which actually helps keep the liquid water liquid so that it doesn't just stop flowing and become an ice cube or a glacier. So one of the best examples of a cryodome is, I think anyway, is on Ceres, and that would be Ahuna Mons. So Ceres itself is a dwarf planet in the asteroid belt. We got very good images of it from the Dawn mission, which was actually in orbit around around Ceres between 2015 and 2018. Ahuna Mons itself is thought to be relatively young, only about 240 million years old. And if it is a cryovolcano, then it is the closest one known to the sun. And that's a really big deal because that might put a limit then on the extent of cryovolcanism, not just in our solar system, but in other solar systems as well. It also teaches us a little bit about what the process of cryovolcanism might be like and what the limits of it actually happening could be. And then in addition to Europa, there are, of course, other Galilean satellites. So the 4 Galilean satellites are named for Galileo Galilei, who was the first person to observe them that Western science recognizes. So we have Ganymede, which is the largest moon in the solar system, actually, and then Callisto. Caitlin actually talked about Io, which is the 4th Galilean satellite. That one is actually so volcanically active that there is no chance of liquid water on it whatsoever. It is the most active volcanically active body in the entire solar system. But Ganymede and Callisto, on the other hand, are not. So what's really cool about these two is that not only do they have one ocean, but we actually think now that they might have multiple layers of oceans and different types of ice. Actually, potentially 19 different types of ices exist in our solar system, many of which are theoretical. So we really only have one type here on Earth, unless we specifically make a different type in a lab. But under great temperatures or great low temperatures and very high pressures, we actually have the potential to have different types of ices form. So that's what we think is going on in these solar system moons. Moving on to the next gas giant of Saturn, we have Enceladus again with its beautiful tiger stripes and geysers at its southern pole. We also have Titan, which again is the moon. It's one of the largest moons in the solar system. It's the largest of Saturn's moons, very thick atmosphere. And again, we see lots of layers of ice and a water ocean. We also see what is known or what is probably the largest cryovolcano in the entire solar system, and that would be Doom Mons, which is in the picture to the farthest right. It's almost a mile tall, and it's 37 miles across. So it's quite enormous. And frankly, I don't know why more sci-fi movies haven't been set at a place called Doom Mons, because it's kind of perfect. So If anybody from Hollywood is watching it, pick here. This is your next. This is the coolest place to be. All right, but moving on to Uranus and Neptune's moons, we actually don't have great information about them because we only sent one mission to look at all of them, and that was Voyager 2. So Voyager 2 got to Uranus in 1986, and it got to Neptune to take pictures of Triton in 1989. So it's been quite a while. These moons could have changed a lot depending on how geologically active they are. But we have Titania and Ariel and Miranda, which are Uranus's moons. We have Triton. Again, Caitlin talked about this a little bit, but it's another spot where cryovolcanism is probably, we have some of our best examples of cryovolcanism from Triton. And then finally, we get out to Pluto, which is also technically a dwarf planet, but it's okay because we love it anyway. So Pluto, of course, Caitlin talked about very well that Pluto itself is probably has a lot of evidence of cryovolcanism. It also has a great variety and distributions of different types of ices. I've been talking a lot about water ice. When I say ice, I do mean water ice, but there's methane ice, that's the CH4 in purple, the nitrogen ice, which is the N2 in yellow, and the carbon monoxide ice, which is the green. And then we have the water ice in the blue in the figure to the bottom right. What we see there is that there's a great variety of these types of ices distributed on the surface, and exactly what caused those distributions is still something that is up for debate. But what I think is coolest about the system is actually Pluto's largest moon, which is Charon. And this is a spread out mosaic of what Charon's surface is. We've only gotten good imaging of about 40% of it, but that 40% is just so cool, because we see there's actually this line that goes through, and I'll see if I can point it out on my screen. I hope you can see my cursor, but if you can't, it's if you're looking in the middle of the screen, you can actually see like a line going through. It looks a little bit jagged, and that turns out to be a big landform on Charon. That north of it, it's more blocky, it's a little bit rougher. There are slightly more craters, indicating that it's slightly older than the terrain to the south, which is much smoother. So maybe the entire southern terrain that we're seeing on this side of Charon indicates that it is a cryovolcanic flow, that there has been some kind of cryovolcanic outflow. And I'm actually on a NASA project now to study cryovolcanism on Charon and try and figure out what exactly happened there. And then there's actually one more stop, and that's something called Haumea, which is a Kuiper Belt object. It too is a dwarf planet, just like Ceres and just like Pluto. And this is work that I have actively done. I've actually just submitted a paper on it in December. So to give you an idea of what Haumea is, it's the fastest spinning large object in the entire solar system that we know of so far. And for something that big to be spinning that fast, it's very unusual. But of course, it's not just that makes it unusual. It is also covered in water ice. So how can something that big and that fast also be covered in water ice? It's been a big planetary puzzle. So what my work has shown is that it likely has a core made up of hydrated minerals. So again, we come back to this idea that water is locked up in the minerals themselves. The type is unknown, but it's probably something like clays. And the most recent models that I was running, especially like the geophysical and the geochemical ones, actually suggests that Haumea is large enough, and it was hot enough at one point to have sustained a liquid water ocean. So potentially now we're looking at this Kuiper Belt object that is orbiting even farther away than Pluto, and it still could be an ocean world, or at least a dormant ocean world. So again, we're pushing the barriers, or we're pushing the boundaries of what an ocean world is and what we think it could be or could have been in the past. And of course, we have a lot of former ocean worlds nearer to us than the moons of Pluto and Haumea. The former ocean world that we like to compare Earth to more often than not is Venus. And that's because it's roughly the same size, it's the same density. It seems like it would be the same, except it's not a good place to live. It is inhospitable, and Earth is clearly not. But to figure out more about Venus. There's actually a couple of missions going there. Again, Caitlin mentioned this in her talk, but this is a brief cartoon from the Da Vinci mission, which is actually going to go through the clouds and land on the surface. So hopefully we get a lot of information from that. And then we have Mars on the right. Of course, Valles Marineris is very visible, and it does have ice at its poles and at very high elevations on some of its taller mountains, but it used to have a lot more water. And the question of what happened to that water and where it went, again, still outstanding questions. So if there's anything that I can say about this talk is that to find what happened to a planet, a big goal is to just follow the water. And we can actually follow the water to other solar systems. So I'm going to now introduce a topic called the habitable zone. So the habitable zone is a region, it's a distance from a star where liquid water would be stable on a terrestrial planet that is about Earth's size. So that's a very important point, that if Earth was in one of these, was around this star and not a star like the one we have, where would liquid water be stable? That's basically what the definition is. And I also want to emphasize that just because something is habitable, a planet is inhabitable, it does not necessarily mean, or it does not mean at all, actually, that the planet is also inhabited. There are a lot of steps that go in between planet formation and the first signs of life. And these are steps that we're still trying to work out. But generally, another good rule of thumb is that if the star is hotter than our star, that the habitable zone is going to be farther out, maybe somewhere like Mars or even the asteroid belt. But then if it's a cooler star, it's going to be much, much closer into the star. So think something like Mercury or even closer to the star. And this is just a metric of where water is going to be stable on a planet's surface. But planets themselves can also move. So they can move in and out of the habitable zone as the star itself is evolving and changing its own habitable zone. So the interplay between planets moving around and the stars themselves quieting down to their present states can change a planet's habitability status. And that's what the graphs at the right are showing, is that planets can move in and out and of the habitable zone, and maybe that changes their capacity to hold life. So we have a lot of evidence, though, that there are many exoplanet ocean worlds. And this is a potentially big area of research because there are just so many exoplanets compared to the few that we have in our own solar system. In fact, I think the total might be over 5,000 at this point. I think it was very close to it a couple weeks ago, so it might be over 5,000 now. So 5,000 other planets is a whole host of new data points that we can characterize and we can generalize, and we can learn a lot about our own solar system by studying the diversity of other solar systems. So I've marked on this graph down here where the Earth is, and Earth is very much in the rocky planet zone, but going up to something that is the size of Neptune, that is has a radius 4 times as big as Earth, we get to something that could potentially be a gigantic ocean world. And it's not something that we have a good analogy for from studying our own solar system. So in a way, we are making very educated guesses based on the data that we have, but there is still so much we don't know because we don't have something good to compare it to. But many people have done a lot of work to try and understand these worlds even more. And one of these work is done by Lene Quick et al., who examined 53 of these terrestrial or rocky exoplanets and studied exactly how much heat that they would produce, either by themselves through things like the decay of uranium in their cores or something like tidal flexing. So the interplay between a planet and its star and how much that generated heat depending on how close it got to that star. So what they've actually found, very interestingly, is that all 53 of these exoplanets should be either volcanically or cryovolcanically active. So again, we have the capacity now to release heat from our solar system or from these planets and potentially even release some kind of slurry. And again, we see this connection between following the water. If there is water in a planet, then there could be life on that planet as well. So determining which of these worlds are cryovolcanically active, specifically which ones could be ocean worlds, gives us a better idea of what to target for future missions like the James Webb Space Telescope or even the Nancy Grace Roman Space Telescope, which will be launching in a few years. That one hasn't gotten up yet. So it turns out that up to about a quarter of all of these worlds that we look at could be ocean worlds. All right, so the big picture takeaways that I want you to remember as you walk away from this talk is that ocean worlds are incredibly common and diverse, and that there are estimates that 26% of these exoplanets could be ocean worlds, of terrestrial ocean planets anyway, and that's wonderfully exciting. So the definition of an ocean world is expanding rapidly, especially as we discover more about our own solar system and what the limits of cryovolcanism are, what the limits of liquid water are, stability are at different temperatures and pressures. And it's very, very cool to be doing this work. That time, along with temperature, composition, and pressure, is just as important of an influence in terms of habitability of a planet. And that planetary analog studies, so looking at what we have here versus what we think is out there, will be increasingly important in the future to try and figure out what is going on in these ocean worlds. So that is the end of my talk. Let's bring on the questions. Ashley, you're muted.
Thank you. That's a pretty important part of speaking. So thank you so much for the fantastic talk. So much, it tied in really well with Caitlin's talk, and I really like how well this worked out for today's show. And we do have already some questions, and also according to some of our speakers, Doom Mons was actually named for Mount Doom from the Lord of the Rings. So,
no kidding.
Yes. And
okay, so Tolkien was really just ahead of everyone.
Ahead of the game, yeah. Okay. So our first question is with I know Caitlin had mentioned the Europa Clipper mission, and is there going to be any tie-in with the Europa Clipper mission to kind of what with the ocean worlds and studying more of I know it's working on Europa. Will that bring, or what would be the importance of that, and what kind of missions does that one really have?
Oh, the most exciting thing that's going to happen from the Europa Clipper mission is that we're going to get much better pictures of Europa. For all that we love about Europa, we really have only imaged 10% of its surface at a resolution where we can figure out what's going on. Everything else is just too far away for us to get a very good and detailed look at its surface. So we're making informed guesses, but it would be really, really great to have better imaging and more details to see what's going on under and try to infer what's going on under the surface. So the Europa Clipper mission is going to launch in 2024. If all goes well, it should get there in April 2030. So we're going to have to wait quite a bit to get more information about Europa. But even having pictures, if we had nothing else, which I hope doesn't happen because I hope we get everything, but if we had nothing else, just getting pictures would be so fundamentally important to try and figure out what's going on and try to figure out how widespread some of these geological processes are.
Awesome. Also, you're welcome to stop screen sharing if you're comfortable doing that. Okay. Thank you so much for that. Our next question: does an ocean have to be water, or can it be methane? Is it possible to have a nitrogen ocean? So on and so forth.
Oh, that's a cool question. So I'm going to say no, it does not necessarily have to be water. I was mostly focusing on water. Well, I guess the official definition is that it is a liquid water ocean, but then we look at Titan, which has its beautiful methane lakes and its methane rain cycle and even weather. And it's hard not to look at that and say, oh, well, there's definitely something going on there when you have liquid anything. We do focus on liquid water because of its relevance for life and astrobiology importance. So sorry if you can hear rustling. That's my cat being very naughty. Right. I don't know what it would take to have a nitrogen ocean. I think it would require very, very low temperature and some kind of pressure. And I haven't actually ever thought about it before, though. Like, under what conditions would a nitrogen ocean exist? That is a really cool thought question. And I would need to know more about nitrogen itself and at what temperatures and pressures it condenses. I'd need one of those triple point graphs to figure that one out.
My apologies. My cat is getting into things like
I completely understand.
So it's a good night for cat owners. Okay, awesome. Our next question, could Jupiter's massive magnetic field alter the behavior or formation of salts in the liquid ocean of the moon?
Yes, it does. So it turns out when the salts get to the surface, they're not quite as red as they are. And I should have mentioned this in the talk, but the redness of Europa has been enhanced. Those are not scientific images, they're more public images. So the color has been changed a little bit, but the salt does get redder the longer it stays on Europa's surface. And that's just a function of how much radiation it has absorbed. It's my cat. I'm so sorry.
No worries.
So it kind of, I don't know how much the radiation would have affected the salts on the inside, aside from just making the induced magnetic field as Europa is orbiting Jupiter. But once the salt gets to the surface, like Jupiter's magnetic field just wreaks havoc on its structure. So that's part of the reason why Europa is so red. That and the fact that it turns out Io is kind of a jerk because it's always spitting out sulfur, and a lot of that actually ends up on Europa's surface too. So it's like a pretty intense sibling rivalry.
Awesome. Okay. Let's see. Let's go back to the chat. Okay. So water drives a lot of the weather here on Earth. How close are we to being able to analyze or observe weather on exoplanets?
Ooh, not super close. I'm so sorry. For most exoplanet observations, and it does depend on how the exoplanet is detected. There are many different ways to look at an exoplanet, and some ways you get different types of information. But if you used a method that looked at the atmosphere, then you are lucky if you get a couple of pixels worth of data. And that couple of pixels worth can be really informative. It can tell you the bulk composition of an exoplanet's atmosphere. And you can, over time, if you got lucky enough to stare at the same exoplanet for multiple cycles, you might be able to see it changing over time. Like maybe it gets a little bit more concentrated, or its opacity changes. So how dark, how well the light passes through the clouds can change over time. And that might be indicative of something like weather, or at least some kind of cloud change happening. But that is if you get lucky, and if you can look at the same exoplanet over multiple cycles, and if you, it's a lot of things that need to happen to line up properly. I'm not saying it doesn't happen, because I do know that there have been studies where people have looked at like night side and day side variations on exoplanets, but it's really hard to do, and it's not something we can do for every exoplanet.
Awesome. Yeah, it'd be really interesting to see the being able to see weather in the future, and just seeing how different weather on other planets would be versus here.
Trust me, I would love that. But some of these exoplanets are so far away that we are still working on getting that technology.
Yes, of course. Okay, let's go here. Also, there have been some requests if your cat is within reach to see the cat.
I do. She's at my feet right now, actually. Is the request to grab the cat and to show the cat off?
Yes.
Okay, come here. No, don't be mean to me. Stop. Oh, she's not happy with me right now. It's because I didn't play with her enough.
No worries.
It's okay. I will grab her when she's calmed down a little bit.
All right. Okay. So can or how could studying the geology of these planets and like the oceans help us understand more about planetary formation?
Ooh, that is a great question. So part of it comes down to when trying to figure out where these snow lines are, especially as a function of the star types themselves. Different stars have different temperatures and they have different stages of their life cycles. So figuring out where our frost line was a big step in understanding planet formation, and especially the dichotomy between more rocky planets and more icy gas giants. That was for our solar system, and it might be different for other solar systems. So we have to go into our contextualization of exoplanet systems with this knowledge in mind that like our solar system is actually very weird. So we are probably everything that we see is going to be very different from what we have experienced here in the solar system. But even knowing details like where the carbon dioxide frost line was and where the carbon monoxide frost line was tells us a lot about the state of our sun when the planets were forming. First forming about 4.5 billion years ago, and then tracing out our sun's life cycle helps us understand where that habitable zone was. So it helps us understand where life might have been. And that's why Venus and Mars are still kind of the big question mark about like, could there have been life there? Maybe, depending on what the sun is doing. And then we have a lot of issues too, because the planets themselves were moving around a lot, especially Jupiter, who at one point was actually, as Jupiter used to be where Mars was. It kind of formed and then it just took a grand tour of the solar system and just eventually ended up exactly where it is. But the thought is that it moving around disrupted a lot of orbits and a lot of dynamics in our solar system. So just trying to understand Jupiter's moons, which should have formed around Jupiter, tells us a lot about where what Jupiter was doing. And Jupiter, being the most massive planet in our solar system, would have had a big and profound effect on what happened to the other planets. So like there is a big compelling reason to study Jupiter, and it's because it's so massive and like a big reason, haha, it's massive. Yeah, that was an unintentional pun. But because Jupiter is thought to have been this giant, like a snowplow of sorts, just like pushing material around the solar system. Studying Jupiter itself is going to tell us a lot about how planets formed, especially because hot Jupiters are relatively common exoplanets.
Yes. Awesome. Okay, let me check really quick. All right. And one last question before we get to, of course, our traditional question. Are there other materials on ocean worlds that could assist in the formation of magnetic fields outside of salts? So you mentioned earlier that since there's salts there, there's going to be a magnetic field. Is there any other way to form a magnetic field without salts necessarily?
A planet could develop its own magnetic field, which would imply the circulation of some kind of metallic fluid, not necessarily metallic iron. Jupiter's magnetic field is actually thought to be a layer of liquid hydrogen, I believe. Gosh, I hope I don't have that wrong. But so that is another way that a planet could have a magnetic field. The reason we don't think that's happening on Europa is because it's pretty small. Europa is actually only about the size of our moon, or Earth's moon that we all know and love. So for something that small to be around something as big as Jupiter, it has a big effect on how much heat is produced, which is why Europa, a big part of the reason why Europa still has a liquid water ocean. But I think it's a little too small to have a a core that is still liquid and moving around. I don't know if that would be true in an exoplanet system, though. We are just at the cutting edge of observing exomoons. There have been a couple discovered. And that's about all I can tell you about them because they're just so small and hard to image.
Of course.
But maybe one day we'll find out.
Awesome. Well, thank you for all those wonderful answers. And of course, we have to close it out with what is your favorite Pokemon?
My favorite Pokemon is Eevee, with a close second of Articuno.
Do you have a favorite evolution of Eevee?
Oh, no. Now I have to choose. This is the worst part about loving Eevee is that like you always have to make it evolve into something, and it's so frustrating. I do really like Vaporeon, and I'm not just saying that because I'm an Icy Worlds person, but Umbreon is really cool too.
Awesome. Well, thank you so much for being able to come and give a awesome talk tonight. And thank you to all those attending our show tonight. And if you haven't already, go ahead and check out our tip war. I'll actually ask you this. I meant to ask Dr. Ahrens also, but between the Heart on Pluto and the Rosette Nebula, which is your favorite Valentine's Day themed astronomical feature?
Pluto. Yeah.
That one I think is our winner here. A lot of people have been choosing our heart shape on Pluto. It's a lovely, and of course the New Horizons was able to give us such a great photo of that. So thank you both for coming by tonight, and thank you to everybody who has attended. Make sure to check us out next month. We will be posting within a few weeks of our next show. So make sure to come back, check us out. And thank you so much for stopping by tonight. And hopefully you all enjoyed our talks and your drinks, and have a good night. Thank you so much.